All right, my friends, we are on page 51. Unless there's any questions from the homework. What? All right, my friends. Yes. E. Like on this page? Yes, we could do E as in Egbert. I don't know where that came from. Okay, yes, we can do E. So I'm going to take a look, and I've got water. Now, water is, we know that water is amphiprotic. And if we don't know that water is amphiprotic, now we do. Yes? Okay. So what water is going to do is going to depend upon what NH3 does. So let's go and look and see what NH3 does on our data pages. Okay? So here we go. First of all, we have an NH3 here. Is that a useful NH3? No, it's not, because it lies down below our acid line, so it is unable to act as an acid. Okay? So NH3 is unable to act as an acid because, look, the arrow only goes towards it. It is not able to give up a hydrogen. So that's useless to us. We're not going to do that. So we have to look for it then on the base side and see, is it a base? There it is. It is a base. Okay? Is it a strong base or is it a weak base? It's in the middle of the table. Everything in the middle of the table is weak. Everything in the white zone is weak. White zone, weak. Gray zone, strong or unable. Yes, if it's on the wrong side, it's unable. We good with that? Okay, cool. Let's go back here. That's not what I wanted. That's what I wanted. Yes. Okay. So this is going to be our base. This is going to be our acid, which means that a hydrogen is going to move from the acid to the base. If we take an H off of water, what are we left with? We are left with OH minus. And NH3 now has an extra H plus, so it will become NH4 plus. Of course. Okay. Now, what kind of arrow should I have in the middle here? Should it be this one-way arrow, or should I make that into a two-way arrow? That should be a two-way arrow because NH3 is a weak base, so it's got to be a two-way arrow. And now we are going to say, all right, my products, who is the acid and who is the base? So you look and you say, if I'm going backwards, NH4 would be giving a hydrogen to OH. So this means that NH4 plus is the acid and OH minus is the base. So now we have to say to ourselves, who is stronger? We're going to compare. I like comparing acids because it's easier. So let's look at water. and NH4 and figure out who is the stronger acid. Oy. Where are we? There we are. Oh, look. Water is an acid, but it is the very, very what? Last acid on the list. That means it's the weakest acid of all the acids before you get to things that can't be acids at all. Okay, so that means water is weaker than ammonium. Ammonium is stronger than water. So ammonium is stronger and water is weaker. What does that tell you about the strengths of the bases? Who is the stronger base? Hydroxide, stronger, because the two stronger things are always on the same side. And here we have weaker. And therefore, which side is favored? Remember, the weak one wins. Yes? So the reactants are favored. What does that mean? Does that mean we have more reactants or less reactants? We have more reactants when it's sitting at equilibrium. It doesn't mean it shifts that way. It means when it's sitting at equilibrium, there is more reactant than there is product. And therefore, your KEQ, is it going to be greater or less than 1? We have more reactant than product, which means KEQ is smaller product over larger amount of reactant. So KEQ is less than 1. Is good? Okay. Any other questions from homework? Moving right along then. So we're not actually going to go through this. I trust that you can read. Yes? There's a couple things, though, I want to get rid of because they don't actually make any sense. So let's go head on to our second page. Okay. It says strong Bronsted-Lowry acid, base, a species that accepts protons 100%. We're going to get rid of the word receptive because receptive means it will receive and acids do not receive. So we're just going to say 100% from an acid, okay? And we're going to do the same thing for a weak Bronsted-Lowry base down here. A species that accepts protons from just an acid, okay? Because receptive acid doesn't make any sense. Conjugate acid-base pair, amphiprotic. Are you familiar with the terms monoprotic, diprotic, triprotic, polyprotic, the hydronium ion? Any questions? No? Okay. We've not talked about this, but this was in Hebden. Okay, so there is a mnemonic here to help you remember the 5 properties of the acids and the 5 properties of bases. 4 of them match up with each other, right? Okay, one of them they have in common. They both conduct electricity. Okay? Another term for conducting electricity is that the substance is an electrolyte. We're going to talk a lot about electrolytes today. We've got our handy dandy conductivity apparatus here that we're going to play around with a little bit. Second thing is the taste. So you'll notice what we have here is we have conductivity, taste, what it reacts with, and then what it does to litmus. And you know what that spells? Control, like on a keyboard, you know, the control key. So you're like conductivity, T for taste, R for what it reacts with, and L for litmus. Okay, those are the four that they have in common. All right, they both conduct electricity. They both have a taste. What's the taste of an acid? Sour. And the taste of a base is bitter. Acids react with bases, and bases react with acids. So good. And acid turns litmus red. If you want to think about it this way, what's going to happen to your skin if you get acid on it? What color is it going to turn? Red, right? Because it'll burn you. Okay, it'll give you an acid burn. So what color does it turn litmus? It turns litmus red. Also, B for blue, B for base. Yes? Also B for bitter. Yes? So B for bitter, B for blue, B for base. And then the only one that's really kind of a little bit weird is the last one. It doesn't match up. Acids react with some metals, not all metals. So if I gave you some gold, it won't react with an acid. You could pour acid on it, it'll just sit there and do nothing. Okay? It could be. Yeah. Okay, so reacts with metals to produce H2 gas. And bases feel slippery, which is why we use them as cleaning products, because they help the dirt slip off our stuff. So you'll notice that ammonia, which is a base, is like in window cleaners and stuff. So if you get that smell of a window cleaner, that's usually ammonia, which is a base, and it helps make it slippery. So slip off the window. Okay. And that's it for that, I believe. And now we are on to strong versus concentrated and weak versus dilute. I would like you to try and explain the difference between strong and concentrated to your partner. See what you know about that already.
Oh, so strong. When you strong is ionized, and strong is ionized. Concentrated is number of particles. Yeah. I love it. I'm just like this.
Okay, strong ionizes completely in water. So if you have HX, use your acid, it's going to, you're going to have a one-way arrow, and you'll end up with H plus and X minus. How much of the HX is left? You have 0% and HX. How much do you have? You have 100%. That's what strong means, okay? Concentrated, on the other hand, means lots of particles in a given volume. So if this is an acid particle, there's lots of them. Lots. Yes? Now, what does that mean about, this one is concentrated. Do we know anything about whether it's dissociated or not if I don't tell you if it's strong or weak? Like if this is an acid and I don't tell you if it's strong or weak, do you know how much of it is dissociated? No, if I don't tell you, you cannot know how much of it is dissociated, okay? Now, dilute. What would dilute look in comparison? Less particles, dilute. Yes, concentrated, dilute. Now, what would happen with a weak acid? Let's say it's HA. Am I going to have a one-way arrow or a two-way arrow if it's weak? It's going to be a two-way arrow. And I end up with only a little bit of H plus and A minus. Yeah? Little. Lots. Yeah? So you can have a solution that is strong and concentrated, or you can have a solution that is strong and dilute. If it is strong and dilute, it just means that all the particles are dissociated, but you don't have very many particles to start with. Okay? You can have a solution that is weak and dilute, but you can also make it weak and concentrated, which just means it doesn't dissociate much, but it has a lot of particles. Okay. Conductivity. Do you guys know why things conduct electricity? How do things conduct electricity? Wires, solutions. So what is the important thing about conducting electricity? I want you to chat about that with your neighbors and decide what you think. Let other people think as well. How do things conduct electricity? What do you know about that already? What do we need to conduct electricity? Yes. Electrons have to move freely. You're partially right. It's not always electrons, though. Electrons will work, but it's not always electrons. What do electrons have? They have a charge. So you need charged things that can move. And in a wire, that will be electrons. Okay? So in the wire, we would have electrons. And they move through the wire. Yes? Because the valence of electrons of metals are held very loosely to their home atom, so they can move from one atom to the next atom. However, in solution, we don't have free-moving electrons. The solutions are not made of metal. But can we have charged particles in solution? Yes. What do we call those charged particles in solution? Ions. They're charged that move. So if we look at HCl, remember HCl dissociates into H plus and Cl minus, and it all dissociates. So you're left with no HCl stuck together. What you are left with is H plus and if you have these two metal plates, what will the metal plate do to those positive ions? It makes them move because what does negative do to positive? It attracts. Okay, so the metal plate, which is negative, attracts the positive ions. Maybe I should have made them red. Maybe I'll do that. Let's make those red. The positive plate what does it attract? It attracts the negative ions. So you can see the negative ions move towards the positive plate, and the positive ions move towards the negative plate, and that is how electricity is conducted in a solution. Now, I don't like that this is acetic acid. I'm going to call it HF instead because acetic acid is too big of a formula to write. Yes? So I'm just going to call it HF. They're both weak acids. And remember, HF, because it is weak, it's only going to dissociate partially. So look, most of the HF is still stuck together. And what can you say about an HF particle? What is its overall charge? HF is neutral. You still have some positives and some negatives, but because a lot of the HF stays together as a neutral particle, it will not conduct electricity as well. The more ions you have, the better a conductor it is. Does that make sense? The more ions, the more charged particles, the better it will conduct electricity. So there's two factors that affect conductivity. Conductivity depends upon the number of ions. What's one thing you can do to make sure that you have more ions in your solution? Say you're given some acids, you're given some strong acid, you're given some weak acid. What can you do to make there be more ions, make it more conductive? Which acid would you use? You would use the strong one, yes? That would give you more ions. How could you make it conduct even better? You put a little bit of the strong acid, what could you do? You could make it more concentrated. You could add more acid to it. That would give you more particles, yes? More ions. Now, let's say I give you a weak acid. Is it going to conduct well or is it going to conduct poorly? It's going to conduct poorly. So your weak acid is a poor conductor. And what you're going to see here in our little pictures is that over on the left-hand side, we have lots of light coming out of the light bulb because we have lots of ions. The weak acid, we have few ions. So it's a poor conductor, so we only get a little bit of light. Would you like to see this in action? Okay, we're going to take a look here at this. This is what we call a conductivity apparatus. And literally, it's just like a light bulb that you have some little metal bits that you can plop into the solution, okay? And I can't tell you, I was so irritated because I went into the back room and for 24 years, all the solutions for this demonstration have been in a box in one place in that room. Do you think they're there today? Nope. But that's okay. We are flexible, and I got over myself and decided, oh, heck, we can just make this happen. Okay, so what I have here is I have some, I labeled my beaker. This is some 1 molar HCl. There's 1 mole of HCl per liter in this little beaker here, okay? And where's my unlabeled beaker, which is my water? I do not know. Is that unlabeled? That is unlabeled. So that's my water. No, that's labeled. So you know what? I'm just going to get a plain beaker of water because I want to start with water. There we go. Maybe this time I'll actually label it water rather than leaving it unlabeled. It's a bit better. So the first thing we're going to do is we're going to start with plain old water. And you're going to decide, do you think it's going to conduct? Is it going to conduct, not conduct? If it does conduct, will it conduct well or will it conduct poorly? Water, plain water out of the tap. Discuss with your partner. What do you think? Are we ready to try it out? Okay, let's go look. 5, 4, 3, 2. Oh, so exciting. Absolutely nothing happens. Why is that? There's no ions. Okay, actually, to be honest, there are very few ions because water does dissociate a little tiny bit, and we're going to learn about that later. But look at that Ka value. 1 times 10 to the negative 14, which means the concentration of hydrogen ion is 1 times 10 to the negative 7, and hydroxide is 1 times 10 to the negative 7. So that means your concentration of ions is like 0.00000001. Or actually, yeah, 0.00000002, because there's a hydrogen and a hydroxide. But like so small, yes, so small. So that's why it does not conduct electricity, because mostly water is neutral, okay? Won't conduct. Only a tiny bit splits apart. All right, back to here. So now let's take a look. We have some, that's our water. We have some 1 molar acetic acid. And we also have some 1 molar hydrochloric acid. Okay, so here's the hydrochloric acid. What do you know about hydrochloric acid? What kind of an acid is it? Hydrochloric is strong. Acetic acid is weak. 1 molar, 1 molar. So the concentration is the same, but the HCl is strong and the acetic acid is weak. So predict to your partner what you think is going to happen when we put the HCl here. Tell your partner what you think. Make a prediction. Are we ready? 5, 4, 3, 2. Whoa. Okay. So HCl, what kind of an acid was it?
Strong.
Strong. What percent dissociated is it? 100%. So 100% of it is ionized. So you have lots and lots of ions, therefore it conducts very well. I'm going to use my water to rinse that off. Where did I put my water? Oh, not that one. Water. There we are. And now we're going to try some 1 molar, same concentration of a weak acid. Predict to your partner what you think it's going to look like.
Wait, what is that?
This is weak acid, acetic acid, CH3COOH. 1 molar. Are we ready? Okay, here we go. 5, 4, 3, 2. What happens? It conducts, but weakly. It is a weak electrolyte. Okay, the HCl was a strong electrolyte. It conducted electricity well. The weak acid is a weak electrolyte. Why am I not getting as much conduction here? Because the acid mostly stays together. It doesn't dissociate into the ions. Okay. Rinsing off again. Where'd my water go? Water. Okay. Now, we're going to see which is more important, concentration or strength. Okay? I am going to dilute my acid by a factor of 10. Okay? So I started with 1 molar. If I dilute it by a factor of 10, what will the new concentration be? 0.1. Yes? So we're going to go with 0.1 molar. Okay, so I took some from here, from the 0.1 molar, and here it is here. Okay, here's my 0.1 molar HCl. Predict what you think is going to happen. Tell your partner what you think. Okay, 0.1 molar. 10 times less concentrated. Ready? Oh, 10 times less concentrated. It is still brighter than the acetic acid that is 10 times more concentrated than this one. Okay? Now, I would like you to figure out, this is a dilution problem for you to do. See if you can remember how to do this. Given 10 milliliters of 0.1 molar HCl, what does my final volume have to be? Oops. To get a final concentration of 0.01 molar. I want you to have a little chat with your neighbor about that. You might be able to do this just by thinking about it, using some proportional reasoning, okay? If not, I will do a very quick lesson on dilutions for you, okay? But see if you can just figure it out. I've got 10 milliliters of my acid. I'm going to actually measure it out right now. No. You are 0.1 mole. There we go. So I'm putting 10 milliliters into my graduated cylinder. There we go. What should my final volume be to get 0.01 molar? I'm going to add water. How many people think they know? A few of you. Okay. To get you on the right track, what would happen to my concentration if I added another 10 milliliters here? So my volume is now 20 milliliters. I double the volume. What would happen to the concentration? It would be half. Yes? Does that make sense? If I double the volume, my concentration will be half. What do I have to do to the volume to get my concentration to be? What fraction is this? This is 1/10. What final volume do I need? I need 10 times the original, so I would need a total volume of 100 milliliters. Does that make sense? Now, if you're like, oh my God, some people are nodding, but I totally didn't get that. It's okay. Don't worry, because I'm going to remind you of the dilution formula. You should work on trying to understand that. Every once in a while, think about dilutions. Dilutions are way more important than you think. Dilutions got me my first job when other people were counting herring larvae. Okay, literally, like they had to sit there at the co-op job. They would sit there and under the microscope, they'd be like 1, 2, 3. For 4 months, they did this. Okay. Me, I got to extract DNA from salmon livers and use some restriction enzymes and run it on a gel, an agar gel, to electrophoresis, gel electrophoresis, and we were trying to figure out if we could tell which salmon were from the same river. Oh, which was kind of cool at the time, 30 years ago, and it's still kind of cool even today. Okay, so I got to do that while my friend got to do 1, 2, 3, because I could do a dilution calculation, because I understood it. Okay, now you don't have to understand the dilution formula to use it, but try to get that reasoning in your head. If I want it to be 10 times diluted, I need the volume to be 10 times more, right? If I want it to be half as concentrated, I need to double the volume. Get that sort of understanding, but feel free to use the dilution formula. It is M1 V1 equals M2 V2. I would recommend writing this down. M1 V1 equals M2 V2. Now, what does M stand for, do you think? Molarity. So, what is our starting molarity? 0.1 molar. That right there is M1. Yes? What's our starting volume? 10 milliliters. So that's going to be V1. Do we have any information about our finishing substance? Yeah, we know the molarity we want to finish with. So this is going to be our M2. And our, what are we being asked for? We're being asked for the final volume, which is V2. So we can take our numbers and plug them into this formula. So M1, 0.1 molar times V1, 10 milliliters. And I'm not going to worry about sig figs here. I'm just going to play fast and loose with them, okay? Equals M2, 0.01 molar times V2, which is my final volume, V2. And then we just have to solve for V2. Okay, so V2 is equal to 0.1 molar times 10 milliliters divided by 0.01 molar. What happens with our units in this calculation? Molarity cancels and we are left with milliliters. And when we plug all those numbers in, we get 100 milliliters. So if you didn't just see the proportional reasoning there, it's okay. You can get to the same answer by using the formula. But like I said, especially when they're nice round numbers like, oh, I would like it to be 10 times more concentrated, or 5 times more concentrated, or 5 times less concentrated. See if you can reason it through in your head a little bit, okay? Just try it every time. And then if you can't figure it out, you can go back to the dilution formula, okay? All right. I'm going to give you, for the weekend, I'm going to give you some dilution stuff to work on. I'll give you like a worksheet that has some of this stuff on it so you can practice with it, because this is a skill that you were expected to learn in grade 11 and you are expected to know it now. But I expect that most of you have forgotten a lot about it. So I'm going to give you some practice to do on dilutions over the weekend. That's going to be your weekend homework. It's going to be just using this formula here. Okay? So after your quiz, I'm going to give you some dilution stuff. That's what you can spend your weekend doing. Okay? All right. So going back, I need to now, that means I need to fill this up to 100 milliliters. So that is HCl. Where's my water? Here's my water. Excellent. Okay. So I'm going to fill it up to 100 milliliters. Oh, not enough. Here we go. Okay. Using a graduated cylinder is one way of doing dilution. You could also use a volumetric flask. Do you remember the volumetric flask? Have you used one yet? Some of you are staring at the volumetric. What? We're going to make a couple solutions, okay, next week, once we're done this quiz. All right, now I need to pour this back and forth into a beaker to mix it a little bit, okay? So here we go, back and forth, mixing it, making sure that I don't have like pockets where it's more concentrated and pockets where it's less concentrated. Okay, that's probably going to be close enough. So here I have my 0.01 molar. Predict what you think is going to happen. This is now 100 times less concentrated. 100 times less concentrated than the weak acid. Are we ready? It's still brighter than the weak acid, yes? Now, I happened to make a 1 in 1,000 dilution for my other class, and so I don't need to make it fresh this time. Where is my 0.001 molar? 0.001. 0.001 molar. Let's see if 1,000 times dilution finally gets us with less conductivity than the 1,000 times more concentrated weak acid. Finally, okay, it's finally less concentrated. So probably somewhere in if I did a 500 times dilution, I might be able to get the same level of conductivity. But the moral of the story is, if we go back to here, oh, not that one, that one. Which is more important when it comes to conductivity, strength or concentration? Strength, okay? So when it comes to conductivity, it matters more whether it's strong or weak. Than whether it is concentrated or dilute. However, you can make a weak acid have the similar conductivity to a strong acid by making the strong acid very dilute and making the weak acid very concentrated. It's not impossible, it just takes a while. Yeah? You just have to do. I'm going to unplug this because we don't want anybody touching live wires. Because you know how electrolytes conduct electricity? Guess what we are made of? Electrolytes. We're a big bag of ions. We are solutions with ions. And so if we touch it and there's any moisture on our skin whatsoever, it will conduct and then it'll go into our body. And okay, so we don't want to do that. I've actually done it before. We had a conductivity apparatus that wasn't very good, and you had to maneuver to get it. Yeah, so it's not fun. It's not going to kill you, but it's not fun. Okay. All right. Please define for your partner what an electrolyte is. This is our next page now. So this is page 55. Do we need a stretch break? Okay, we need a stretch break. We're gonna go, everyone's gonna go outside. Come with me. Everyone's gonna go outside because it's nice out. Come. Come. We're all outside.
It's simply not drinking. Sipping.
Of course you would know.
Should try. Have you ever tried this sliding down this slide and then have like a little and that was some of the touch on your person like all of it. I did that now.
Okay, we're gonna do one more thing before we start again. We're gonna wiggle our fingers. Wiggle the fingers up above your head. Now I would like you to wiggle your toes. And now I would like you to wiggle your ears. Who can wiggle their ears? Yeah? Anyone else can wiggle their ears? You guys can't wiggle your ears? Who can wiggle their ears? Seriously. Nobody? I got like 1, 2. No? Can you wiggle your nose?
Yeah.
Try wiggling your nose. Ears? I don't know. Can you see my ears moving?
Yeah. I can see it from here.
No? Anyway. Try it. If you've not tried it, try it. Try wiggling your nose and wiggling your ears. Give you something to do in your spare time when you're not studying chemistry, right? Okay. What is an electrolyte? You know what? I'm just going to tell you because we need to get through this. An electrolyte is a substance that does what? Conducts electricity. And where does it conduct electricity? It conducts electricity in solution. Therefore, what must it contain? Must contain ions. Okay, so we have a little strong acid here, and we have a little weak acid. Aren't they cute? They're in little Erlenmeyer flasks. We have the strong acid and the weak acid. And the strong acid will ionize completely, okay? All of the acid particles will dissociate. So it's going to be all here, and we're going to have none of this. You do not need to memorize these 6 acids. Why? They're on the table. But if you ever get to the point where you do need to memorize them, you can remember Chloe Kleiberson, okay? ClO4, ClIBr, SO, and then N. There should be an O at the end, but Kleibersono sounded stupid. So I brought no clean clothes. You don't need to do that. This is because I use the same thing for my AP students, okay? And they do have to memorize them for that exam. Okay. Anywho, the one thing I did want you to notice is that only one of the hydrogen from the H2SO4 comes off. The HSO4 remains intact. Please go find HSO4 on your data table. Now it actually shows up in 2 places. It shows up over here. Am I interested in that one? No, why not? Because it is too weak to act as a base. It cannot accept protons because the arrow only goes that way. So I have to be interested in the other one, which is here. Now, what kind of an acid is HSO4 minus? It is a weak acid. It's in that white middle section. So W for white, W for weak. Yes? Gray section is for the strong ones. Okay. So here we go. So HSO4 is a weak acid. So it mostly stays together. It mostly stays undissociated. So that's why we don't bother taking off the second H. So that's our strong acid. And if we zip on down to the bottom of the page, you can see, oh, look, every single one of these is ion, 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 ion. Okay, all ions. Compare that with our weak acid, CH3COOH. Oh, look, how many ions do we have? We have ion and we have ion. Mostly not ions, right? Mostly neutral particles. Okay, and we're just going to take a quick look at our data pages again. Okay, because I want you to take a look at all of the Ka values. Our strong acids, we have the Ka is very large. We have hydronium, the hydronium ion, which has a Ka value of 1. So the conjugate acid of water has a Ka value of 1. But everything else has a Ka value of less than 1. They're all small, right? Ka of weak acids are all less than 1. What does that tell you about the concentration of reactants and the concentration of products? Concentration of reactants is greater than the concentration of products. And remember, the reactants are neutral and the products are ions. Yes? So what that's telling us is that the neutral things are more than the ions. All right? So if we go back here, you can see, oh, look, neutral things are more than ions. So far more is undissociated. So we have lots of this, and we only have a little. So the equilibrium lies far to the left. Is good? Okay, so in other words, strong acids are going to be strong electrolytes. Don't confuse strength with concentration. I just have this picture here because I figured it would look nice. We've got like, oh, look, I have a strong concentrated solution and I have a weak concentrated solution. Who are the ions in here? I got, oh, everybody's an ion. Ion, 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 ion. Everybody is an ion. So many ions. Over here, it's the same concentration. I made sure the number of particles were the same, but I have much less ions, so the conductivity is much lower. We have a strong acid, now it's dilute. But we still have ion, 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 ion. Whereas over on the right-hand side, if we have a weak acid and it's dilute, I just have ion, ion. Okay? I think I'm just beating a dead horse at this point. I think I'm saying the same thing over and over again. So the moral of the story is that strong acids are strong electrolytes and weak acids are weak electrolytes. And because I always get someone who asks this question, no one is ever going to ask you if a dilute strong acid is a strong electrolyte. That's just a stupid question. Nobody's going to ask you that. It just, yeah. Okay, it's a semantics game. Okay, it's all about words, right? We don't want to, it's not conceptual at that point. They might ask you to rank solutions in order of highest conductivity to lowest conductivity. So you can say, oh, these acids are both strong, but this one is more concentrated, therefore it will be more conductive. It'll be a stronger electrolyte. I got a strong acid and a weak acid. The strong acid will conduct better than the weak acid. That's all. Okay? Bases. Bases actually require you to know a little bit about solubility, so we're going to throw that out the window because we've not done solubility yet, and we are going to say for the purposes of Unit 4, all metal hydroxides that I will give you are soluble, 100% soluble. So no matter what your solubility table says, the ones that I give you are 100% soluble. Okay? For Unit 4, metal hydroxides metal OH, are completely soluble. So don't think about it too hard. Don't be like, oh no, calcium hydroxide is low solubility. Well, to be honest, calcium hydroxide has a medium solubility. So if I don't put too much of it into my solution, it will completely dissociate if I haven't saturated the solution. Okay, so if I only put 0.01 moles into a liter, it will all dissociate. Okay, so the moral of the story is all you really need to know at this point is that strong bases are strong electrolytes. And you should know that the only two strong Bronsted-Lowry bases are NH2 and O2. How would you recognize those? They are on the bottom right of the table. Okay, those are your two Bronsted-Lowry strong bases. But for the most part, all Arrhenius bases are strong. All Arrhenius bases are strong. Why? Because metal hydroxides, which are Arrhenius bases, are completely soluble. Can you guys give me an example of a metal hydroxide? NaOH. Great example. Love that one. NaOH dissociates into Na plus OH minus. And you end up with 100% here. And you end up with that all gone. Yes? So it dissociates completely. It is a strong electrolyte. Therefore, strong acid is a strong electrolyte. Strong base is a strong electrolyte. You do not need to worry about this. Cross it out. That's for AP. I should have got rid of it for you guys, but I didn't think that far ahead. Strong Arrhenius bases dissociate completely in water. And we didn't make it this far with the other class, so you're not going to need to know anything about alcohols for the quiz because we're not going to make it there. Okay, so you don't need to know about alcohols for the quiz, so this stuff is not on the quiz. But I do have one more question for you. If you were to take a look at lithium hydroxide and calcium hydroxide, and let's say you had 0.01 molar LiOH, and you had 0.01 molar CaOH2, which of those would conduct better? The second one, because you're going to get 0.1 molar of the lithium and 0.1 molar of the hydroxide. Yeah? Because this starts at 0.1 molar, and this is a 1-to-1-to-1 relationship. But if we start with 0.1 molar CaOH2, we end up with 0.1 molar calcium and 0.2 molar. I guess I should have said 0.1 because I've now dropped to 0. Sorry about that. 2 molar, which means that I have more ions, therefore it is more conductive. I'm not going to ask a lot of questions about conductivity on the quiz. Okay, so I know we spent a lot of time on it today, but it is like sort of the last thing that we have learned about. So I'm not going to focus on it on the quiz. It's going to be more the stuff that we did the previous day. So what you'll want to review for your quiz is 4.1i. That's lots of practice. And you can review the vocabulary in 4.1g. Okay? And that's it. Yay, we finished in time. That was exciting.